Subsea pipelines transport crude oil through extreme environments. Wax and asphaltenes can precipitate, creating. Understanding this deposition is crucial for flow assurance.
Welcome to this video on organic deposition, specifically focusing on wax and asphaltenes within subsea architecture. This is Module 5, prepared by Dr. Qureshi from National University of Singapore. He specializes in the area of flow assurance and provides consultancy on complex problems. In this first part, we will explore wax or paraffin deposition, covering its thermodynamics, mechanisms, and profiling. Wax deposition occurs when high molecular weight alkanes in crude oil precipitate due to cooling as fluid travels through cold subsea pipelines, leading to flow restrictions. The wax appearance temperature, or WAT, marks the point where wax crystals begin to form. Managing this is critical for pipeline design and flow assurance. Unmanaged wax deposition can be costly, reducing pipeline capacity by up to 30% and potentially leading to severe blockages requiring expensive remediation. Paraffin crystallization is driven by temperature gradients, composition, and pressure effects, as shown in these solubility curves. Several factors influence the WAT, including the fluid's thermal history, light ends content, water cut, and the presence of asphaltenes, which can accelerate crystallization. The primary mechanisms for wax deposition are molecular diffusion, shear dispersion in turbulent flow, and gravity settling in low-velocity regimes. Initially, wax forms as a gel-like layer. Over time, an aging process occurs, where lighter components diffuse out and the deposit hardens, making it difficult to remove. Industry employs various testing methods to evaluate wax, including microscopy, calorimetry, cold finger tests, and flow loop testing for dynamic conditions. Now we move to Part 2, asphaltene deposition. We will discuss stability envelopes and the impact of pressure depletion. Asphaltenes are complex, polar, heavy fractions of crude oil containing heteroatoms and trace metals defined by their solubility class. Often called the cholesterol of petroleum, asphaltenes are insoluble in light alkanes but soluble in aromatics, existing in crude as a colloidal suspension. Sera analysis breaks down oil into its components. Generally, a higher ratio of resins to asphaltenes contributes to a more stable crude system. Finally, the asphaltene stability envelope is driven primarily by pressure. Instability peaks near the bubble point, where gas expansion reduces solvating power. Moving to the impact of reservoir depletion, the asphaltene onset pressure, or AOP, serves as a critical threshold. If reservoir pressure drops below this, irreversible precipitation occurs near the wellbore, permanently damaging permeability. As fluid flows up the production tubing, pressure drops continuously. Crossing the AOP envelope triggers precipitation, resulting in hard, coal-like deposits that resist mechanical removal and often require chemical or coiled tubing interventions. Precipitation can be triggered by several factors: pressure depletion towards the bubble point, fluid commingling with incompatible light oils, or gas injection, which acts as a precipitating anti-solvent. Next, we examine Part 3, mitigation and remediation, focusing on thermal, chemical, and mechanical strategies. For wax management, the primary defense is maintaining temperatures above the WAT. Key thermal methods include wet insulation, high-efficiency pipe-in-pipe systems, and seabed burial or trenching. Thermal management is split between passive insulation, which preserves heat during production, and active heating systems like direct electrical heating, which prevent blockages during extended shutdowns. Chemical treatments include solvents like xylene for cleaning, pour-point depressants to manage wax crystal growth during shut-in, and asphaltene dispersants to maintain colloidal stability. This table compares wax and asphaltene inhibitors. Note the different chemical applications required for each type of organic deposit. Mechanical remediation, or pigging, uses pipeline inspection gauges propelled by fluid pressure. This is a standard method for removing wax, utilizing scrapers or brushes for tougher deposits. Successful pigging requires optimizing frequency to balance costs and risks. Note that while effective for wax, standard pigging is generally ineffective for hard asphaltene scale. Ultimately, flow assurance is about more than preventing blockages. It is vital for guaranteeing the economic viability of deepwater assets over their entire lifecycle. The management lifecycle progresses from initial appraisal and fluid sampling to design, ongoing operational maintenance, and finally, late-life management of water cut and pressure decline. Integrated flow assurance combines thermal control, precision chemical injection through umbilical networks, and regular mechanical pigging to safeguard production. It is important to note that chemical additives often represent the largest portion of remediation OPEX. Accurate modeling of WAT and AOP is essential to avoid unnecessary chemical overdosage. This concludes Module 5. Our next session will focus on inorganic scales and sand management. Thank you for watching this module. If you are interested in consulting, research collaborations, or technical training, please feel free to reach out via the contact information provided on screen.